Chemical equilibrium. Looking at what we've discussed so far, reaction spontaneity in terms of Gibbs free energy is essentially looking at whether a reaction is going to quote-unquote go or not as written. So it's looking at whether a reaction is going to proceed in the forward direction. Kinetics looks at the reaction speed, that is to say, the rate with which the reaction occurs, producing products. Equilibrium now is going to explore what we would call the extent of the reaction. It's going to explore how far a reaction proceeds along its reaction coordinate pathway toward product. Reactions are generally treated stoichiometrically in that we treat them like if they proceed entirely to the product, and there is no reactant remaining. However, in reality, we will have a mixture of products and reactants in essentially every reaction that we deal with. We can quantify this ratio of product to reactant by what we call an equilibrium constant. In any of our systems, we're going to have a little bit of reactant left, even if our reaction has gone essentially to product. Now, chemical equilibrium looks at both the forward and reverse rate of a reaction being equal. This occurs at the point where the free energy of that reaction is equal to zero. In a system that is a dynamic equilibrium, because our forward and reverse reaction rates are equal, yet still occurring, there is no net overall change in concentrations. However, individual particles are still able to react forward and backward. If we have a chemical equilibrium, we require a closed system. If I can remove product or reactant from the system, I am not going to have a closed system. For a closed system of reaction A plus B making C plus D, this reaction as expressed is a reversible reaction, and it is considered reversible because we have this double-headed arrow from reaction to product. Not all product is going to form in this case. The reaction can take product that can reform reactant and continue the reaction in the forward direction. We can influence how a reaction occurs by various conditions that occur in the equilibrium. This is generally referred to as Le Chatelier's principle, that if I take a system that has already come to equilibrium, I'm going to be able to affect how that equilibrium is established and continues to be established by outside influence. This is something that we'll talk about later on. But we know that a reaction overall is going to vary with the conditions. If I look, for example, at the reaction that occurs in your bloodstream, the reaction of hemoglobin to bind oxygen to it. In a situation with low oxygen content, like the rest of the body outside of the lungs, our reaction equilibrium is going to favor the reactant side, such that we're going to find more of our hemoglobin without oxygen added. In a situation with a high concentration of oxygen, like inside the lungs, we're going to favor the right-hand side, the product side, with hemoglobin complexed to that oxygen. So we can have this dynamic achievement back and forth of equilibrium, and the actual position where the equilibrium lies can change based upon the conditions we're looking at. Now, for dynamic equilibrium, technically speaking, every reaction is potentially reversible. Some reactions essentially don't reverse because of very high reverse activation energies, but we can consider all of our reactions to be a competition between forward and reverse processes. If I look at this then for our A plus B reaction, the forward process is A plus B yields C plus D. The reverse process is C plus D yields A plus B. This is signified with that double-headed arrow. In this, the equilibrium occurs where the rate is equal between these two reactions. So we quote-unquote go to completion only if I have essentially undetectable reverse process. If I consider an analogy for this, if I have a situation where we have apples fallen from a tree, if I have a young boy who lives on the side of a fence where the apple tree is located, whose mother tells him to clear out all of the rotten apples that have fallen. If the boy is rather lazy, he might consider just taking those apples and throwing them over the fence. Now let's consider in this situation that on the other side of the fence lives an older man. Now as the boy begins to throw these apples over the fence, the older man is not appreciative of this, and he'll go outside and toss the apples back to the boy's side. This obviously is a bit of a far-fetched analogy, but assuming that this occurs, as the young boy throws the apples over and the old man continues to throw them back, we'll know that the boy most likely is going to have a significant advantage in doing this. He is able to move much more quickly, most likely, than an older man will, and so the rate with which he can throw the apples over the fence is going to be higher than that of the older man throwing them back. But as he continues to throw the apples over the fence, he's going to have fewer and fewer apples on his side, whereas those on the other side of the fence are going to increase in number. Even though the older man cannot throw the apples as fast as the young boy can, as the apples begin to pile up on his side, the rate with which he can get to an apple and throw it over the fence versus the boy having to move around the yard to try to find the few remaining apples that are there, are going to cause the rate with which he throws the apples over the fence to become faster relative to the rate that the boy throws the apples backwards over the fence. Conceivably, at some point, they will be able to throw these apples over the fence at the exact same rate where the concentration of apples on both sides has become static. This is kind of how an equilibrium works. Another way that we can think of equilibrium as an analogy is that if you're running on a treadmill, you're moving your body such as you want to move in the forward direction, but because the treadmill is working against you, your body doesn't actually move translationally in space, it stays in one position, but you're continuing to run. So you're going to continue to move, but you're not gaining any latitude in your movement. You're going to continue in one spot. Both of these analogies are very similar to how a reaction equilibrium works. In a dynamic equilibrium, at any temperature, we're going to have the same ratio of product to reactant. So our ratio of product to reactant is a temperature-dependent process. But for a specific temperature, we expect to have the same ratio. For a closed system of A yielding B, if I start with nothing but reactant and no product, over time my reactant is going to be consumed and my product is going to form. And eventually it will come to a point where their concentrations no longer change. This is the point at which we've established equilibrium. If I look at the reverse process, where I start with nothing but product and all reactant, once again, we're going to have a situation where we're going to change concentrations. Now in this case, we're going to have a decrease in the concentration of product and an increase in the concentration of reactant, but eventually once again we come to equilibrium where the reactant and product concentrations become static. In the first instance, the reaction in the forward direction starts off faster than the reaction in the reverse direction. In the second instance, the reaction in the reverse direction starts off faster than the reaction in the forward direction, but in both cases, the forward and reverse reactions ultimately become equal. If I look at the way that we describe this, we can express a equilibrium by what we call the law of mass action, where the product molarities are raised to the stoichiometric coefficients that are in their equation as a ratio of product to reactants. So for a generic equation, 2A plus B makes A2B. We would have, in this instance, a very similar situation to kinetics for a single-step pathway that involves the products too, and a constant that we call Q or K. So if I'm looking at this Q or K, whichever term I'm using for the constant is going to be equal to the concentration of A2B divided by the product of A raised to the second power times B. So we've got the reactants raised to their coefficients as the denominator and the products raised to their coefficients as the numerator. The equilibrium constant is a quantitative relationship to this ratio. For our 2A plus B making A2B, we've got that K value. For a rate, the forward rate is going to be 2A plus B yields A2B. That gives us a rate of K times A squared times B. For the reverse process, A2B will yield 2A plus B with a rate of a reverse constant K prime times A2B. At equilibrium, these two rates are equal, and where these two rates are equal, I can divide the rate constants and the concentrations to isolate the rate constants on one side and the concentrations on the other. Looking at K versus K prime then, we get the equilibrium constant as the ratio of K to K prime. So the value we know of any rate constant is temperature dependent, and this is why the overall equilibrium constant K is temperature dependent. This then produces a equilibrium constant of K being equal to the concentration of A2B over the concentration of A squared times the concentration of B. This is the equilibrium expression for this particular reaction. We call this the law of mass action, this relationship of product to reactant raised to stoichiometric coefficients producing an equilibrium value. At 25 degrees Celsius, some examples of this, nitrogen plus oxygen yielding to nitrogen monoxide, has a Kc value of 4.5 times 10 to the negative 31. The reaction of nitrogen with hydrogen to produce ammonia has a Kc value of 4.1 times 10 to the 8. We see from this that we've got a very small value in the first reaction, and that very small value indicates that the reaction denominator must be much larger than the numerator. Because the reaction denominator is much larger than the numerator, we can conclude that the reaction is reactant favored. In the second process, the value is large, and from this large value we can conclude that the numerator is much larger than the denominator, meaning the reaction must be product favored.